Welcome to The Explainer. Okay, today we are diving into an absolutely fascinating and, frankly, incredibly high-stakes topic. We're going to decode the exact engineering parameters you need to stop catastrophic sand production in some of the harshest gas fields on the planet. We're specifically looking at extreme conditions, like the ones found in Kazakhstan. If you're dealing with high-velocity gas extraction, the data we are going through today is literally the difference between a well that produces for decades and one that just tears itself apart.
So here is the million-dollar question we have to answer. Why do traditional sand screens fail so catastrophically in gas wells? We are talking about terrifying stakes here. You can have a perfectly functioning well, and then, boom, due to a slight miscalculation, you experience sudden, massive production drops. We are talking about shredded downhole equipment and millions of dollars lost simply because the environment down there is so incredibly unforgiving.
When we think of oil wells, we generally picture steady fluid dynamics, right? Oil flows relatively smoothly, and the wear on the equipment is gradual and, for the most part, predictable. But gas wells? Oh man, that is a completely different beast. You're dealing with violent, high-velocity gas that carries sand at absolute breakneck speeds. It's essentially a massive sandblaster operating deep underground, causing extreme, rapid erosion. You just cannot apply oil well logic to a gas well problem.
Fatal challenges of gas sand.
Look, there are four main threats we absolutely have to manage. First, the high flow velocity of the gas itself. Second, the severe physical erosion caused by that high-speed gas. Third, the chemical nightmare of high concentrations of hydrogen sulfide and carbon dioxide. And finally, the migration of fine silt. Because the gas is moving so fast, it easily picks up and drives microscopic silt from deep within the formation, which then physically wedges into and totally plugs up traditional screens.
Get a load of this specific number, less than 44 microns. We are talking about fine silt and clay particles thinner than a human hair. These are the silent killers of gas well permeability. While traditional screens might stop your large grains of sand, they are entirely blind to these sub-44 micron particles. These tiny specks swarm the screen, pack tightly together, and literally choke the life out of the well.
Parameter 1, fluid dynamics.
The absolute core requirement, like the mandatory starting point, is PSD, or particle size distribution. And to be clear, this isn't a guess. It's exact compaction sieving test data of the actual formation sand returned from the target gas layer. We need to know those D10, D50, and D90 values. Without this precise curve, it's impossible to design the specific gradient sand control structure of the metal foam required to capture those microscopic particles without absolutely choking your gas pressure.
Next up in our fluid dynamics data is the WGR, the water-gas ratio. This measures the water production per 10,000 cubic meters of natural gas. Now you might be wondering, why do we care so much about water in a gas well? Well, it's because of droplet impingement erosion. In a high-velocity two-phase flow, those water droplets act exactly like high-speed liquid bullets hitting the screen. We have to calculate that impact force.
And finally, for this section, we must capture the gas well's absolute open flow, or AOF, and the design pore flow velocity. By knowing the exact speed the gas is moving, engineers can calculate the precise kinetic and erosive energy that the metal foam screen is going to be subjected to over its entire lifetime.
Parameter 2, corrosive environments. Now let's talk about the hostile, wet gas environment these screens have to survive in. We aren't just dealing with sand here. We are dealing with highly acidic sour gas. We have to map out the partial pressures of hydrogen sulfide and carbon dioxide. We also have to assess the risk of elemental sulfur deposition, high chloride concentrations, and the terrifying risk of hydrogen-induced cracking, which is literally where the metal itself becomes brittle and just snaps under stress.
So the solution to this underground chemical warfare is purely metallurgical. Advanced metal foam screens utilize an integrally formed, weld-free, pure nickel alloy. As this highlights, that pure nickel layer ensures thermodynamic stability. To put that into perspective for a second, while traditional stainless steel might show severe pitting or cracking within months in high H2S concentrations, pure nickel maintains a near-zero corrosion rate under the exact same extreme acidic stress. It's a real game changer.
Parameter 3, mechanical constraints.
We absolutely need the exact wellbore specifications. What are the gas-type premium connections required? What is the maximum deviation angle of the pipe? The crucial point here is mapping out the dogleg severity, or DLS. Think of it like this. High-velocity gas acts like a race car. It wants to travel in a straight line. If there is a severe bend in the pipe, the gas-carrying sand will violently crash right into the wall of the screen at that specific bend. We have to predict exactly where that erosive force is going to concentrate.
Coping mechanism of gradient pores.
Notice this critical threshold right here, 16%. Metal foam screens are engineered to maintain a 16% high open porosity flow area. This is a massive leap forward in the tech. It vastly outperforms traditional screens, ensuring that even as the foam captures particles, there is always an open, unchoked channel for the gas to escape.
Think of this metal foam not as a flat window screen, but as a complex 3D labyrinth. It uses a multi-layer gradient cage structure. The pores get progressively tighter as you move deeper through the metal. This gradient traps that microscopic 44-micron silt deep within its matrix, while that 16% open porosity allows massive, high-velocity volumes of natural gas to flow right through without any drop in production or pressure. It's brilliant.
Custom screen selection logic.
Okay, here is how all this data actually builds into an actionable installation and operation workflow. Step 1. You must pull the PSD curve and the fine silt mass. This is the mandatory first step before any physical manufacturing can even begin. Step 2. You overlay the gas-fluid dynamics, the absolute open flow, and the water-gas ratio to calculate erosion thickness. And Step 3. You finalize the design against the physical wellbore mechanics and the chemical sour gas profile to make sure you're choosing the exact right pure nickel alloy.
When you master those 3 data parameters, it directly translates into customized hardware capable of surviving for decades. Look at the Central Asian gas fields. Every single deadly challenge, from the sub-44 micron silt to the extreme acid gas to the violent droplet impingement, it all has a direct, engineered solution inside the metal foam architecture.
Which brings us to the ultimate question for any petroleum engineer or field manager tuning in today. Are your field's exact engineering parameters truly ready? Do you have the granular PSD, the precise fluid dynamics, and the exact sour gas profiles required to survive high-velocity gas extraction? Because in this extreme environment, guessing simply isn't an option. Thanks so much for joining me on this explainer. I really hope this deep dive into gas well sand control completely changes how you look at your wellbore data.